hello, Jimmy.
Hello,
Hello. Who else am I helloing right now?
Amy, Axel, Woody, Angela.
Yeah. All right. So all those hellos.
Luis.
What the? I saw him a minute ago. No, I saw spare parts. All right. Anyway, sequences. This is a new chapter, and this is it's one of those things that actually, when I was in college, and it was one of those things that actually got me big time. Like, that was my Achilles heel. This chapter was my Achilles heel. So going over this, I'm going to try and explain it in a completely different way than my instructor, because he wasn't very good. And I'm going to do my best to make it so it's going to conform to what you guys understand. So if there's part of it that you're not getting, I need you guys to speak up and ask about this, because, like I said, this is the part that I feel weak about in this math course. So, all right, definition. Sequence is a function whose domain is a set of positive integers and whose range is a subset of real numbers. Now, so basically domain, positive integers. So what does that mean? Numbers greater than 0. Okay, like counting numbers, right? Okay, that's what we're doing, right? Okay, and a subset, which means after I plug those in, the range is going to be a subset of real numbers. So do I have to get integers out of it? No, I'm going to get some nasty numbers. But guess what? Still works. Okay, to get an idea, okay, let's take a look at this graph of f of x equals 1 over x for where x is greater than 0. Okay, there's my subset of positive, my set of positive integers, right? Where x is greater than 0. So right here, then as I plug it in, it's going to be 1, 1, right? This is my first point because I'm plugging in 1. Then when I plug in 2, it's going to be 1 over 2, right? Because I'm plugging in for the x. And 3, 1 over 3, 1 over 4, 1 over 5. You notice it keeps going, right? As I keep going. So my domain of this is my positive integer. So I'm starting here and I'm going this way. And the range would be a subset of that. So it's going to be lesser than what I have. So what that means is, if you notice in this case right here, what is it going to? If I were to ask or say, hey, what's the limit of this going to be? What would the limit of this thing be? 1 over infinity, right? So it's eventually going to what? 0. Okay, so the limit as this goes, keeps going, so it's going to end up becoming 0. So that would, we're going to get into those, and that was going to converge to the number 0. Okay? So, easy way to obtain terms of the sequences of S of n equals f of n. So, f of n means what? Plug in n for your variable, right? Okay, so equals 1 over n. In general, whenever a rule for the nth term of a sequence is known, then any term of the sequence can be found. We also use the nth term to identify the sequence. When the nth term is enclosed in braces, like we have here, is going to equal my function, which is 1 over n, where n is my integers that are going in there, and this is where it's going to. As I go into infinity, as it keeps going, there was my pattern right here. The sequence is my y values that I'm getting out of it. Okay? So it's the output of all these. Does that make sense? Pretty basic, right? Okay. So, now, in this case right here, write the first 3 terms of each sequence. Okay, where's my sequence starting at? Starting at 1, okay? Starting at 1, so starting at 1. So starting at 1, because I'm stating it that it's going to start at 1, so it would be 1 over 3 times 1 minus 2. right? Okay, so the next one's going to be 1 over 3 times 2 minus 2. And the last one's going to be 1 over 3 times 3 minus 2. So in my first term, that's going to give me what? 3 minus 2 is 1. So 1 over 1 is 1. Okay, good. All right, next one's going to be 6 minus 2 is 1 over 4. My last one is going to be 1 over 7. Pretty straightforward, right? Are we okay?
Yeah.
Okay, all right, next one. So see then, so now for this one, let's do the same thing. But this one's not stated, so it's implying that it's going to start at 1. So your first term would be your 1. Okay?
So it's not stated and it's automatic.
Yeah, it's going to be 1. So your first term should be the 1. Okay, so it's going to be, let me see, 2 times 1 minus 1 over 1 cubed. And it's 2 times 2 minus 1 over 2 cubed. And it's going to be 2 times 3 minus 1 over 3 cubed. So let me see, the first one, what are we going to get? 2 times 1 is 2, minus 1 is 1, over 1, which is 1. Okay, so we have, okay. Okay, so it's going to be, let me see, 3 over 8. Okay, and my last one's going to be 5 over, there we go. Yeah? Okay.
Where's the This is great.
What? It's conceptually, my instructor was so bad that I was like, why and what and for what reason am I doing this? And he was not very good at explaining it. He wanted to always sound very, very smart. He could not actually tone down the terminology or the mathanese to just so I could understand what he was saying. So anyway, so let's go ahead and do this one. Find the first 5 terms of this one. Okay, so if n is 1, so this is going to give me, let me see, that's going to give me what? Negative 1, right? And this is going to give me times 1/2, which is negative 1/2. The next one. This is going to give me 2, right? So 2, negative 1 squared is 1, right? So it's going to make it a positive, isn't it? All right, and then it's going to be positive 1 times 1 over 4, which is 1 over 4. So if you notice what's happening into my signs here, they're switching signs. So now when is it switching signs? Every other, but now that's, you got to be very precise in what you're calling.
It's
Odds and evens, right? So an odd integer is going to give me what? A negative. While I have a even integer, it's going to give me a positive. Those are the terminology I want you guys to try to, okay, because it's going to ask the same type of questions. Okay, the book is even going to say something like that. All right, so let's go with the next one. So cubed would be 3, right? So it's going to be, that's going to be an odd, so it's going to be a negative 1, and that's going to give me 1 over 8. So it's going to give me negative 1 over 8. Do you need a bigger eraser? Need an eraser? You good? Okay. All right. So let's go with the next one. 4th term. So that makes this piece right here positive. And then this is 2 to the 4th, which is 16. Positive 1 over 16.
Yeah.
Okay, good. All right, and 5th term. So odd, so it's going to be a negative 1 over 32nd. 2 to the 5th is 32. There we go. First 5 terms of the sequence. Pretty straightforward so far, right? Okay, good. All right, finding the nth terms of a sequence. The rule defining a sequence, S of n, is often expressed as explicit formula for its nth term, S of n. There are times, however, which a sequence is indicated using the first few terms, suggesting a natural choice for the nth term. So, find the nth term of the following sequences. Assume that the indicated pattern continues. So it's what?
E to the n.
Okay. So this would be A of n is going to be what? E to the n over n. Pretty easy, right? This is the part that I actually like because I like patterns and trying to figure it out. It's puzzles. You ready? B to the n.
1 over 3 to the power of n minus 1.
1 over 3. You said 1 over 3.
To the power of n minus 1. Because the first term is 1 over 1. Second term is 1 over 3 to the power of 1.
Okay, so it's 3 to the first, right?
3 to the 0.
Oh, no, nothing.
They're over in Hagen's room.
Who is?
Hagen's.
Oh, the kids?
Right
Four
there.
terms 3 to 3.
Okay, what is,
0.
okay, 0. So if it's n is 1, what's 1 minus 1? 0, right? Anything to the 0 power is 1. So that would give me, now, what's a good way to try and help with this? You have a guess, right? Start putting your number to see if it works. Okay, that's always works out. You know what the first 4 numbers are here, so you could try and put them in. So let's see. So I got to get 1 over 1, so yes, I get that. Okay, what about 2? So 2 minus 1 is 1. So 3, so it's 1/3. There we go. Okay, next one's going to be 3. Okay, so that's going to be 3 minus 1 is 2. So 3 squared is 9. 1 over 9. There we go. And 4. 4 minus 1 is 3. 3 to the third is going to be 27. So 1 over 27. Hey, that does work. Good job. Okay. Now let's take a look at C of n. That one should be easy. And it's great.
Yeah, 2n over
let me see. At 1, it'll give me 2 over 2. At 2, it gives me 4 over 3. At 3, it gives me 6 over 4. Okay, and at 4, it's 8 over 5. Okay. All right, how about that?
Oh, jeez. I am not walking up.
Oh, what's good?
I was just gonna say thanks for the noodles.
Oh, hey, you're welcome.
Yeah, they're delicious. For lunch.
Oh, it's Friday, so gotta do my extra class.
Oh, right on. Well, hey, have a good week.
Oh, me too. All right, so next one would be where are we at? E of n. So E, come on, pen. E of n. So I made it a point to point something out earlier.
So 1 to the negative n, because that's.
Ooh, hey, that's gonna help me alternate, right?
Yeah. Is there any other way to alternate, other than just that?
With the exponents, you can incorporate the exponent, or you can incorporate the negative into your problem, if you want to there, but, you know, it's more hassle. So- No, the back end of the pen comes off, so. Anyway, plus I like with the masking tape, it has like a better feel. Yeah. Alright, so we're gonna say that this is gonna be -1 to the n, right? And then it's gonna be what?
1 over n.
Okay, so it's times 1 over n. Does that work? Did you check them?
So 1 and then a negative 1 and 2. Oh, shouldn't it be negative 1?
So it should be a -1, right?
Yeah, but you read that. No. Oh yeah, times that. Yeah. Wait. No. Negative 1 to the n is fine. It's negative 1 to 1. Wait. That changes it.
That's such a big
1 to the n. Negative 1.
How did you fix it over here? How'd you fix it on b to the n?
No, what you had should be fine.
What I had should be fine?
Negative 1 to the power of n times negative 1 over n. Because the third term becomes negative times 1.
So you're saying -1 to the n times 1 over n?
But negative 1.
Negative?
Or n minus 1,
N minus 1.
the exponent.
N minus 1 right here?
Yeah.
Or yeah.
Okay, so if I do n minus 1, okay, so that would give me a 0. So that would make this, anything to 0 is 1. And then I get over 1, which is 1. 2, which would be, there we go. Took care of that, right? Okay, so you're saying that if we put a negative here also, if I would have just put a negative right here, that would have been a -1, right? Negative makes it positive. So either way would have worked to make this one work out. You see? Or is anyone questioning? Are we okay with that? Okay. So let's take a look as E. Now how about F?
Complete the pattern.
Mm-hmm. And so after this unit, you think your IQ is going to go up? Yes.
One more brain cells will die.
Whatever it is, it's over n, so it's something over n. Because, and then for all the odd ones, the top has to be the same as the bottom. I don't know how that happens.
That should be an N.
Wait, should that be positive or even? N is positive. N is
Even, sorry. I don't know what I was thinking. Even, sorry.
Are you allowed to do that?
Yeah.
Can't you just do an infinite amount of brackets then? Like, if n is 1, then it's 1. If n is 2, then it's 2.
Okay, so since this is an example, you can show this. Okay, we had something that is consistent right there in between, and not really a way to try to get those.
If there's a problem like this on the AP test, will they accept what we have?
Yeah,
Yeah.
this is actually solutions for this. Okay, but I have not delved into the BC testing very much. So, anyway. Okay, so, convergent sequence. As we look from left to right, because we're starting at integers that are positive, so therefore, I'm going from 0, right, or 1 to the right, moving to the right. Look from left to right, points on the graph sequence, d of n, equal to 2n over n plus 1. Figure where, okay, we get closer to the line, y equals 2. If we look far enough to the right, the points would appear to be on the line, y equals 2. Although in reality, the points are always very, very small. Distance below the line. In fact, right here, we can show that the limit for this one right here, so as n gets huge, it's getting closer and closer to 2. But as we're doing this, n, okay, n is the number that I am actually plugging in for each one of these. So as n is going to infinity, as I have an infinite number of sequences here, as it's going to the positive infinity, it's going to converge. So the word's going to be converge. It's no longer just the limit, it's converging to. It's going to that number 2 in this case. Does that make sense? So yes, we're taking the n going to infinity. The limit as n goes into infinity of this, we're going to get the value 2. Make sense? Okay. Definition convergent sequence. Let L be a real number and let S of n be a sequence. The sequence S of n converges to the real number L, because L is supposed to be the limit, right? Capital L, limit. Yes? Okay, good. If for any number epsilon greater than 0, there is a positive integer n, capital N, so that in this case, we're going to have the absolute value of S of n minus L, whichever my limit is going to be less than my epsilon for all integers where n is greater than n, capital, where n is my positive integer, right? Yes? Okay, positive integers for right here. Okay, so if S of n converges to L, then L is called the limit of the sequence. If it converges to that, that's going to be the limit of the sequence. We write that limit as n goes to infinity, s of n is equal to that limit. That's my L that goes in there. So if it is less than, then it should be. So if the sequence converges and is said to be convergent, otherwise it's said to be divergent. Okay. There is a little thing right here that is actually real important. What does little n represent? The term, right? So, but those are the terms that are going in, right? Where n is going to be, the capital N is going to be the number that my output is giving me. Right? The capital N is going to be the output of it. So it's going to be it's basically like the f of n on this one. Okay? Now, I want you to conceptualize this because my instructor could never explain this in basic English. So, as n, okay, little n, as I keep plugging that in, for it to be convergent, it's got to converge, right? So, let's say my n equals 3. Okay? So, for it to converge, it's got to be less than the value of the previous. Or somewhere in between. There's an absolute value that it's going to be eventually trying to squeeze it into. I think I have a graph for this. Here it is right here. So, I have values over here, and so from here, it's on the left-hand side, it's way up and down. So I'm starting where n, right here. My epsilon would be my plus epsilon, so this is my s of n minus capital L absolute value. Okay, is going to be less than my epsilon. So if I were to rewrite this, this would be negative epsilon is going to be less than s of n minus L minus less than epsilon. So it's going to be between there. So eventually, as I put in a number, it's got to be less than the previous number, right? Or it's got to somehow be squeezing in between there. So since this one is an alternating series in between positive and negative, right? If you notice, they keep getting closer and closer to that limit, the L. Because epsilon, whatever it's going to be over here, it's got to be somewhere squeezed in between there. That's the point we're trying to make. As I plug in a number, because if it's not converging, let's say n squared. So let's say s of n equals n squared. I know this is not going to converge because I'm giving you one that's going to be divergent. Okay? So if I plug in my numbers, so it's going to be 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9. So now, if you notice, my n's, as they keep going in, are not being squeezed into a little thing, right? This is divergent. So as it keeps going in, it keeps getting bigger, right? Keeps getting bigger. It's going outside of those values. It's greater than the values that I previously had for this. So this is going to be divergent in this case, yes.
So we have to stay within the negative epsilon to positive epsilon range?
Yes, and this is going to be for it to converge.
What if it goes below the negative epsilon? Is that possible?
Mathematically, it's going to be somewhere in between here. Mathematically, it's going to be somewhere in between here. So in the case, once we have something that is convergent, it's going to be, so epsilon is just right here, the lowest and the highest right here. So it's plus and minus whatever it is that's going to shift up and down. Remember, squeeze theorem. So squeeze theorem is going here, like that. So it's squeezing somewhere in between there. Okay?
Where does epsilon come from?
Epsilon. Okay, so now as we're doing this, we're going to find an epsilon and we have a delta for this. Okay, I'm going to give you a new page right here. So I'm gonna give you a graph. This is my function. So now we're gonna get, let's say here, and I have L here, and I have my X here. Okay? So, in this case, I am going to so up here above the L is going to be positive. So it's going to be L plus epsilon. This is just mathematical theory. It's proof for this. Okay? Below the L is going to be, so it's going to be L minus epsilon. Okay? And I'm going to have that there because I also have this over here. So when I'm dealing with this over here, I also have, okay, I have my delta x, right? So it's x, then it's going to be over here, which is x minus delta x. And over here on this side, it's going to be x plus delta x. Remember, delta x is the difference. It's the change in that one, right? So somewhere in between here, so as I get closer and closer to this, so let's go back and do my little graph thingy that I did for my squeeze, right? So we said it's something like this, like that. Okay? So as it is getting closer and closer here, that means that this is getting closer and closer to what my limit is going to be at some value here. Okay, but since this is not going to go to that number, okay, it's not going to go to the number. So the limit, so as this is going to be going to infinity, right? It's going to be going up and down, squeezing to some little spot right here somewhere. And it's going to get my delta x so tiny small that it's going to be basically that number. That's where the epsilon comes from. Epsilon is whatever my limit plus and minus. Where my delta x is going to be plus and minus over there. And we're going to get more into that later on. But like I said, you know, this is one of the concepts that my instructor was like, you should know this. Come on, you got this.
Did he really have that accent?
Yeah, he did. All right, we love you, Filippo. Yeah, you are right. Okay, nice guy, really was. But, he, you know, like, anyway. He wasn't the one that tormented me, but, you know, this guy. Anyway, all right, we okay. So, do you understand the epsilon, where it's coming from?
Yes.
Michael.
Yeah.
Because you had your hand up, but he answered, or he asked first.
My question. So to go back to the other one. So that's for an alternating one. So for the non-alternating, would it just be like?
It's still going to be plus and minus epsilon. So whatever we have, it's going to be somewhere in between this window.
Okay.
So the window in this case, it's eventually going to go, and it's got to be somewhere in between there.
And so for the non-alternating ones,
It's still going to be, yeah, it's still the same thing.
And then like for the other one, it would be.
It's still the same thing. We're still going to the number, even if you're going to it from above only or below only. So it's going to be the same thing. But this is, the best example is going to be this one right here, because you guys know squeeze theory. It eventually squeezes down to be some number. Because when we did the limits of those, you're like, hey, it's this number here, right? Okay, that's what I'm trying to get at. All right, so this one would be divergent. Well, that somewhere in between is going to work. Okay, beginning terms of a sequence can be ignored when determining the convergence or divergence. Because right here, all this over here, it was outside of that, wasn't it? Okay, first couple terms, if you notice, it wasn't even part of that. So 1, 2, 3, 4, eventually gets down to a point where this is where n was less than equal to my capital N, where at this point right here, n is now greater than this. So if it's some weird number that your exponents finally have to build up high enough to be greater than, so think of it like one of those throwing problems or something like that, or you know, like ones that you're starting off with some value and it's eventually going to your velocity starts off at this and it's eventually going to start coming down. You know, you have an initial velocity that takes it up, but no matter what, if you get enough x values out of it, your velocity is still going to go down at that point. Okay, so yes, it goes up a little bit, but then you're going to go down at the end. Okay, yes?
So if one term goes outside of the bounds, then
You're still fine. Because if you notice right here, the beginning terms of a sequence can be ignored. So right here, this is where the part they're referring to.
What about like the terms afterwards?
Terms afterwards, then all of that, then it's going to be divergent. If it doesn't stay there, it's going to diverge. So if it's not staying somewhere in between there, and like you have like a jump over here or somewhere at the end, then that means it's going to diverge. Okay, it's not going to go like you wouldn't say that has a limit anymore, right? Just think of those as being a limit of a function. Okay? All right, so where n, little n, is less than or equal to capital N, distance between the points n and s of n, and the line y equals L may or may not be less than epsilon. Okay? Might be outside of those. Okay? Outside of those bars. Crap, right here. Might be outside of those bars. These terms have no effect on convergence or divergence of the sequence, but if a sequence S of n converges, then for any epsilon, you know, somewhere in between there, any epsilon greater than 0, there is an integer n, capital N, so that for all n, lowercase n, it's going to be less than capital N. Okay? So then it's going to start squeezing in between there, right? So my integers that are going in are going to be greater than what's coming out of that. The distance between the points n and s and n and the line y equals L remains less than epsilon for all n greater than n. Yes?
Is there a way to find n, big N?
Yeah, we're going to do those. So we're going to do those. We're going to find something for this. We're going to find something for this. So that's the next problem. Show what sequence converges. Okay, use the previous thing, which I underlined right there. Okay, so my sequence is going to be what? C. So it's going to be S of n, right? Minus L less than epsilon. So I'm going to say that absolute value of C minus, what is the limit? C is less than epsilon. Okay, so C minus C gives me 0. So now I'm going to have that 0 is going to be less than epsilon. So epsilon has to be greater than 0. Now in this case where I have that n is going to be greater than n.
So any number after C.
Any number for that, it's always going to be that.
What if little n is
Okay, so now think of it like this. Okay, you ready? Let's put in some numbers for this. Let's put in some numbers for this. So let's start this sequence. Is there an n there? Is there an n in my S of n? No. So this is going to be C, right? What's my second term? What's my third term? Fourth term? What's my fifth term?
Billionth term C.
It's like the Russian CCC.
Okay, so my epsilon right here is going to be greater than 0 because that's what we're looking for there, right? So converges for any epsilon greater than 0. There is an integer, okay, if a sequence converges, okay, for any epsilon greater than 0, there's an integer, capital N, so that for all lowercase n, okay, it's going to be greater than capital N. Okay? For that, did we get that? Say yes. Yeah, we did get that. So then I'm okay. I did get that. So epsilon is going to be greater than 0. Yes? That's what I was going for. Did that make sense now? Or did I totally screw you up? So that rule right there es muy importante. It's very important. If a sequence converges, epsilon has to be greater than 0. Okay. Now, you ready for the next one? Okay. So, all right. So now this one does have an n. So let's go in. So now, what is this one going to look like? Absolute value 1 over n minus. Say it. 0 less than epsilon. Okay, so let's go ahead. So it's going to be, I'm going to end up with 1 over n is, absolute value 1 over n is less than epsilon. Okay, so now I don't like those terms. So now I got to change it up now because I have n. So I need it to be. I got to figure out something for this. So now I'm going to change this up a little bit now. So let's do a little bit of algebra. Okay, because I know when I write an absolute value, it means that there's going to be a positive and negative, right? So I know that I'm going to have a negative epsilon is going to be less than 1 over n. That's less than a positive epsilon, right? Okay. So now I'm gonna try and algebra this now. Okay, I don't like my n right there. So I'm gonna multiply all sides by n. Let's do that. Okay, multiply all sides by n. So now I'm gonna have negative n epsilon less than 1 less than n epsilon. Okay. Now, I want to get those epsilons out of there because I want to talk about just the n values that I'm going to have. So, how would I get rid of the epsilons?
You can compare like the first one and the third one, and just
Divide by.
Yeah, by epsilon.
Divide. Okay, we're going to do that. We're going to basically, since I have 3 parts here, it's the same thing. So divide all by epsilon. So it's going to be negative n. And this is n 1 over epsilon less than n right there. All right? And so now from there, now I have it set up. I want to make sure I do not screw up this part right here because this is the pain right here. So I get that.
Don't you have to find an n value where n is greater than the output? In an input value that's greater than the output value? And can you just plug that in?
Wait, hold on. Like I said, I don't want to screw this up because have it here and greater than 1 over epsilon
That's a good.
for all. Okay, and then we go with the next part, which is going to be for all n. Okay, for all n for the previous, right? So for all n that is greater than capital N, just want to make sure I don't screw that up. So for n that's greater than capital N, right there. So I want to try and make a inequality statement for this. So I know that epsilon, right, in this case right here, it's going to be this, so it's going to be where I have 1 over n, because all this right here is going to be my less than epsilon. Oh, crap. I don't want to screw this up now. I'm going to. I swear, I know I'm going to screw this up. 1 over n.
What are we trying to find?
No, we have to try and show that it's going to be convergent. So it has to be.
The question of the day.
No. Okay, so now since I have all this right here, so since I have this right here, okay, it's going to be less than epsilon. Okay, so there's 1 over n, right? And then my other side, which is going to be this piece right here. So I could rewrite this as an inequality also. So if this is 1 over lowercase n, right? So hold on. I'm going to show the algebra because that's where I don't like screwing this up. And come on. Okay, so capital N. All right, so divide by capital N. All right? Okay, divide by or multiply by 1 over little n.
Can you put it lowercase n?
Hmm?
This is messing me up.
No, the big one is the capital N.
Okay, so
We're like medium-sized ends now.
We have 3 size items.
okay, you ready? All right, so n greater than.
Sorry for making you have to change.
It's fine. Okay, so we're basically going to multiply this one. Okay, it's divided by capital N, right? And multiply by 1 over capital N. Divide by lowercase n. Multiply by 1 over lowercase n. So those cancel. So I now have 1 over lowercase n is going to be less than 1 over capital N. So I have now changed it so that this is going to be, because bigger numbers, right? Bigger numbers are smaller fractions. Yes? Bigger numbers are smaller fractions. So now I could rewrite this as where I'm going to get, insert page. Okay, so I'm gonna get smaller fractions, so I'm gonna have my 1 over capital. Okay, and then I'm gonna have my 1 over capital, so that's gonna be less than my epsilon, which is less than my I know, right? So this is going to be 1 over n less than 1 over capital N. Yep, that's what I had.
Are they both?
Now there's an M.
Did you do that on purpose?
So can someone
Which is less than,
trying to find.
which is less than, which is less than my epsilon. I'm sorry, like, you know what, this is, the struggle is real here.
This condition.
Now, from the condition right here. So, because I started off with this, I'm telling you, this is so ridiculous. I'm like, okay, so we got this. We got this, right?
My soul.
That's what happens when I live stream.
Someone's saying putting it over M.
Could have swore someone just divided by 0.
Wait, does epsilon actually does epsilon actually have a value?
Nope. It's some plus or minus value.
But it's greater than 0, just remember that. It's any number greater than 0.
Okay, so these are lower cases, right?
It can be.
So, again, I will reiterate, absolute value, 1 over n. This is my lower, right? Okay, so epsilon is there, right? And I know that epsilon has to be greater than, you know, whatever value there. Yes? Okay, good. So I also know that my n is greater than capital N. Okay, in an inequality, right? In an inequality. So, go back to the algebra, right? And it turns out that 1 over capital N is going to be greater than 1 over lowercase n, right? Okay. So in this case, since I know I have this here, right? I have this here. Say yes.
Yes.
And because I'm using this right here, right? Yes? Okay. I'm using those two things right there. So 1 over n, lowercase, is going to be less than 1 over capital N. But all of that there still has to be less than epsilon. That's what I did on that other page right there. So 1 over, because my inequality here, right? 1 over n, lowercase, is less than 1 over capital N. 1 over capital N, because of this over here. It's got to work for it to work out. I'm not dealing with any numbers here, so I'm just talking about if I have a function with some more values, I'm going to eventually get something out of this. So that's supposed to be, from here, it's going to be less than my epsilon. And in that case, for this to work out. For this to work out. Okay, for all this to work. For all this to still work out, that for this, it has to do what? It has to go what?
Converge.
It has to converge. Okay, it has to converge to 0. Okay, for this to work out, it all has to converge to 0. So this is, if I had, please, one of these days you'll be like, oh hey, where's some numbers? Okay, if I had the numbers to go along with this, you'd say, oh yeah, okay, that does work. Okay, let's say 5 and 4. Capital N would be my 5th term, right? No, lowercase n would be my 5th term, where it would be greater than 4, right? So from there, it would be 1 over 5 is going to be less than 1 over 4, which is still in turn going to be less than whatever my epsilon is in my sequence, because my epsilon is going to eventually get down to that number. So on a graph, it would be the terms for this, and it's eventually going down to that number, down to 0. Does that make a little bit better sense if I throw in some numbers? So if we said this was 5, 4, 1 over 5 is less than 1 over 4, which also should be less than my epsilon. And then in my graph, okay, I have my, in this case right here, I have my limit is L here, because it's going to 0. I have my, this one, which is my minus epsilon, and I have my plus epsilon. So my dotted line here, so everything in between there, it's going to be in between this. To get my epsilon somewhere in between there. So 1 over 5. So this is going down to be 1 over 4, right? Okay, and which is still less than whatever my epsilon is. So my numbers, if they work out, because this is greater than this whole thing is going to converge, and all of it's got to be less than my epsilon, which is going to be in between these two bounds. Little bit better sense? Throw in some numbers, yes.
Should I erase the?
No, it's. I'm telling you, this is one of those things that's just wonky because there is no real numbers, and it's a new thing about talking about, like, what the hell? Where did epsilon come from? What? I didn't even know epsilon was a letter.
I saw the answers for Unit 8 in the back of the book, and it was just words.
Yeah.
No numbers.
But is the inequality where it's like the negative n is less than the 1 over epsilon?
Yeah, this is still right.
No,
That-
the one before it.
The algebra part.
Oh, the algebra part, it's still fine. It's still fine. The algebra is still true, but I replaced it at the wrong place. So I shouldn't have actually broken it up like I did. I should have actually just went to this from my original.
So I can't erase it. It's like it's stripping me.
Here. Have my special sushi eraser. Okay. All right, so that's going to be example 4, and then we'll do 5 Monday. Okay? So,
Man, I feel bad. Well, actually,
like, share, and subscribe.
like the people